For over 2,000 years, many construction problems remained unsolved. Using only a compass and straight edge, ancient mathematicians could bisect a given angle, but they couldn't trisect. Given a square, they could construct a square with double the area, but not a cube of double the volume. They could construct regular triangles, squares, pentagons, pentadecagons, and double the number of sides indefinitely. But they couldn't construct anything else. Why not? Some of these problems are tantalizingly similar to ones with known solutions. What makes them so different? It took until Gauss in 1796 to add another regular polygon to the list, when he proved it was possible to construct a heptadecagon. I made a whole video on his solution and the historical reasons why it might have taken so long to get there. In this video, we'll show exactly which polygons are constructible, why angle trisection and cube doubling are impossible, and shed some light on the overlooked mathematician who did it. We know that using a compass and straight edge we can make any integer length, we can add, subtract, multiply and divide any two lengths, and we can also make the square root of a length. Therefore, the numbers we can construct are those which can be built from the four basic operations and square roots. We showed how to do these constructions in the last video, but what we didn't show are that these are the only operations. For example, who's to say that we can't construct cube roots? We just haven't figured out how yet. We'll address that now, and to our rescue, it's our old friend Descartes. It's easy to poke fun at Descartes for his personality, but he is the father of analytic geometry, so credit where credit is due, he did some amazing things. Now, when we use a straight edge, we are just drawing a line segment, and when we use a compass, we trace the arc of a circle. Therefore, any new points can only arise from a line meeting a line meeting a circle, or a circle meeting a circle. Descartes' insight was to embed geometry onto coordinate axes and describe geometric entities algebraically. We take it for granted today, but this was an enormous leap. As we know now, the equation of a line can always be written in the form y equals mx plus c, and a circle in this form, where these objects meet over the x's and y's coincide. Essentially, in each case, we have to solve a pair of simultaneous equations. I'll spare you the details as it's some pretty routine but messy algebra, but the bottom line is this. In each case, the solution, and that is the new point that we're creating through the intersection of these objects, is built using only the four basic operations and square roots. So no matter how crazy your construction, you cannot escape the fact that any new point you create will be the outcome of the four operations and square roots. No cube roots, no fifth roots, and so on. But you might be hesitant to rule out cube roots altogether. So we can't make, say, the cube root of 2 directly. But who's to say we can't string together a clever chain of the four operations and square roots in such a way that we end up with the cube root of 2? Well, to that I say welcome to the rest of the video. This very question motivates everything that we're about to dive into. And it's kind of the same story with regular polygons. Last time we saw that constructing, say, a regular 7gon is equivalent to building this 7th root of unity, a complex number z such that z to the power 7 equals 1. Now we just argued that we can't construct 7th roots directly, but we did see that the 17gon was possible. We strung together a bunch of square roots in a clever way that gave us the 17th root of unity. What makes it possible in that case? The answers, I'm afraid to say, aren't easy. It'll be a difficult climb, but we'll take things step by step, making sure we lay enough groundwork to actually build the steps on which we'll walk. Some of that groundwork was covered in the last video, but I'll always remind you of the necessary facts, so this video can be viewed as a standalone episode. Let's get into it. As I outlined in the last video, these problems all rely on being able to construct certain irrational quantities. In this next section, we'll get a grip on what sort of irrational quantities we're even able to make. So using just the four operations and the integers, we can build any rational number. So Q, the set of all rationals, will be our foundation. These are all my rational numbers here. And we know that with a compass and straight edge, we can also square root, producing certain irrational numbers. But we're not going to consider square root as one of our operations. Rather, when we make an irrational square root, we will add it to our set. And essentially when we add an irrational, we'll track which numbers it is now possible to make during a given construction. So for example, let's start with q, and let's say that we make some irrational number the square root of r. Now the square root of r is one of the numbers I can play with to make more numbers. So what is the full extent of numbers I can now produce with the 4 operations q and root r? Well, I can add, I can subtract, I can multiply and divide, but notice that no matter what I do, I just wind up with a rational number plus a rational amount of root r. To get some intuition for this, we often think of the real numbers, rational and irrational, as part of a number line. The rational numbers are speckled along like a foamy mass, extending into every crevice, but still leaving holes. Those holes are the irrational numbers, and now when I drop in one single irrational and still take the set to be closed under the 4 basic operations, I now have much more stuff. And as it turns out, every element in this new set can be reached by taking some rational number plus a rational amount of that irrational. It's not unlike the complex numbers, where we start with the reals, we introduce I, and now every complex number can be written in the form a plus bi, where a and b are real. Here I'm just dropping an irrational into the rationals. That irrational is root r, and every number in this set can be written in the form a plus b root r, where a and b are rational. The point is, though, that I need 2 rational numbers to describe a number in this set. So we might think of this set as like 2 copies of q, irrational plus a rational amount of that irrational. We might think of this new set as being twice as large as q. What if I threw in another square root, say the square root of s? And let's assume that root s isn't already in the first set. Well then now I have more numbers that I can reach. I can start with any rational quantity plus an amount of root r, but also plus a rational amount of root s. But also remember, once root r and root s are in my set, I can multiply them to create root rs. So I actually need 4 rational numbers to describe a number in this set. We could think of it as 4 copies of q, and in some sense we could think of it as 4 times bigger than q. The actual language we use is that these irrationals extend q, they give it a bigger reach. This one we call a degree 2 extension, and this one with root r and root s we call a degree 4 extension. Now, one question you might have is, how do we know we can't simplify something like this further? Like, what if there was some combination of root r's and root s's that allowed us to describe root rs, and so it's actually a degree 3 or a degree 2 extension in disguise? Well, hold that thought for just one moment, because I want to know what happens when I add a cube root to q. Now, we know we can't construct cube roots directly, but let's just see what happens if we extend q by, for example, the cube root of 2. Well, as always, I can take any rational plus any rational amount of it, but remember that once the cube root of 2 is a member of our set, we can multiply it by itself to create another irrational number. This didn't happen before. When we included something like the square root of r, we just get one irrational number appended to q, whereas here, the cube root of 2 sneaks in another irrational along the way. So we need 3 rational numbers to describe a number in this set. We call it a degree 3 extension. We need a rational number, a rational amount of the cube root of 2, and a rational amount of the cube root of 4. And again, just like with this up here, we might be wondering why this can't be simplified further. For example, how do we know that there isn't some amount of a plus b times the cube root of 2 that could describe the cube root of 4? How do we know it's not really a degree 2 extension in disguise? We'll address that now, because we do want to clarify why extending by a cube root feels different to extending by a square root. As it will turn out, this is crucial to understanding why cube roots cannot be constructed with a compass and straightedge. So we'll start with this degree 4 expression, and we'll show that it isn't really a degree 2 or degree 3 expression in disguise. What does it mean to simplify an expression? So more generally, let's take irrational numbers alpha, beta, and gamma and scale them with rational numbers a, b, and c, and add them. So you can imagine this taking place inside some extension of q. And now if we could simplify this, that would mean that we could write it in terms of just 2 irrational numbers. Let's call those irrationals delta and epsilon. But notice that delta and epsilon must be in here, so they can be written in terms of alpha, beta, and gamma as well. If we substitute these in for delta and epsilon and simplify, we realize we've actually not written it in terms of two irrationals at all. So introducing these two new irrationals doesn't work. So how else could this be simplified? Well, it could be simplified if one of those irrationals was actually a combination of the other two in disguise. Without loss, let's assume that some amount of gamma, call it d gamma, could actually be written as E alpha plus F beta. Well, that's equivalent to saying that gamma can be written as a rational amount of alpha plus beta by dividing through this d. For the sake of brevity, let's just write E over d as g and F over d as h. They're all rational numbers, so it doesn't really matter what I call them. The point is, though, that I can substitute this in for gamma, and I can tidy it up to two terms. So this whole thing is simplifiable so long as I can do this. But this is true if and only if I can find rational numbers that scale alpha, beta, and gamma to make 0. Now this seems like a pointless reiteration of this condition up here. If I can write gamma in terms of alpha and beta, then of course I can just rearrange it to make it all add to 0. The advantage of this is that here the statement is sort of centered around gamma, but what if it's easier to write alpha in terms of beta and gamma, whereas here it's a sort of symmetric condition. As it will turn out, this condition is much more useful. But the point is, this expression is simplifiable if and only if I can find rational numbers to scale the variables to get to 0. In the biz, we call these types of variables linearly dependent. But don't worry about the language. The key is that if we want to show something can't be simplified, we need to show that it is impossible to find rational multiples of them to sum to 0. That is, the only way this expression could be 0 is if all of those rationals are 0. So for example, I claim that a plus b root r cannot be simplified. If it could, it would mean that I could find some rationals c and d, not both 0, where I scale them and sum them to 0. But now make root r the subject of this, and I find that the square root of r, an irrational, is equal to minus ac over bd, which is rational, a contradiction. Notice also that I showed that a and b root r are independent, but all I needed to do was show that 1 and root r are independent. Like clearly, if I can scale a and b root r with rationals to get to 0, then clearly I can scale 1 and root r with rationals to get to 0, and vice versa. Now let's go ahead and fulfill this promise to show that this expression up here cannot be simplified. Well, it can be simplified if and only if I can find rationals that scale each term and make them sum to 0. Now this final term has a root rs, which is really just root r times root s. Now I can factor out the root s and make root s the subject. Then we can rationalize the denominator and factor out the root r. But now notice what's happened. We've got root s is equal to a rational number plus a rational amount of root r. We assumed that that wasn't possible because we said that root s was going to be something new to the set. So this is a contradiction. So this can't be simplified, and this really is a degree 4 extension, and the pattern continues. You can use an inductive argument to show that throwing in another square root that isn't already in there will double the degree. Therefore, q extended by k independent square roots will have degree 2 to the power of k. So now what about this situation with the cube root of 2? Why can't we simplify that? Well, this situation is a little more complicated, but it is much more illuminating. To motivate the next section, I'm going to hint at the punchline so you can see where we're headed and not get totally lost. We know that with a compass and straightedge, we can only build square roots, and that throwing in a bunch of square roots extends q by a degree a power of 2. But if a cube root extends q by degree 3, which isn't a power of 2, then with some more work we can show that the cube root of 2 cannot possibly belong in any of these extensions, and thus isn't constructible. That's where we're headed. The question is, what if the cube root of 2 could be simplified, that it is maybe a degree 2 extension in disguise? How do we show that? Well, that's the crux of what we'll cover next, developing yet more theory which can then be applied to solve the polygon problem, cube doubling, and angle trisection. So the goal is to show that these three terms are independent of each other, that they can't be simplified. Well, we're going to show this in Q, and remember they can be simplified if we can find rationals that scale them and sum to 0. Now let me rewrite the cube root of 4 as the cube root of 2 squared, and now we notice something. If this statement were true, it would mean that the cube root of 2 is a solution to this quadratic equation with rational coefficients. But is that possible, given that we already know it's a solution to this cubic polynomial? As it turns out, no, this is not possible, but it is surprisingly difficult to see why. But because it's so difficult, it will force us to deepen our understanding and develop some theory that'll generalize to many other problems. Just a quick reminder of some terminology: a value that we insert into a polynomial to make 0 is called a root. So I'm going to call them roots rather than solutions from now on. So we already know that the cube root of 2 is a root of this polynomial here. If I could prove to you that it isn't a root of any polynomial with a smaller degree, then we'd be done, because this case up here would be impossible. That's the key idea. That which is a solution to a cubic can't usually be sneakily obtained as a solution to a quadratic. So picture this. There are a whole raft of polynomials with the cube root of 2 as a root, right? Well, imagine listing them all in order of degree. Well, then there must be one of smallest degree, right? Well, let's call that f of x, and let's say it has degree m for minimum. There might be others of the same degree, but we're just saying that m is the smallest possible. And because I'm bored of saying the cube root of 2, let's just call this alpha and save ourselves a few precious syllables. So if f of x has degree m, it must look like this, where m is the highest power of x that appears, and all of these coefficients are rational. Now, anyone who has ever dealt with polynomials knows that they are easier to work with when the leading coefficient is equal to 1. We can actually assume that without loss of generality. We'll simply divide through by this leading coefficient. This is fine because if alpha is a root of this, then it is certainly a root of this. Now, in the biz, we call this one a monic polynomial, from mono meaning one, and ic from polynomials, get it off me. And you may not realize it yet, but we've actually created something very special. We call this the minimal polynomial for alpha. And why the minimal polynomial? Because it is actually unique. That's right, there are no other degree m monic polynomials with alpha as a root. And if you don't believe me, let's imagine that there's a different one with degree m monic and with alpha as a root. Now subtract them. These x to the power m's will cancel, and for the other terms we just subtract the coefficients. But now this new polynomial must have alpha as a root. And now we've discovered that alpha is a root of a polynomial with a degree less than m. That's impossible because m is the minimum. The only way this can be the case is if h of x is the 0 polynomial. But if that's the case, then f must equal g. Hence, they were the same all along, and so f is the unique minimal polynomial. There's a couple more properties of the minimal polynomial that we're going to need going forward. I know this might feel like a weird departure from the realm of compass and straightedge, but bear with me, it is all going to come together. So another consequence of this minimality is that it can't be factorized. Since school, you've known how to factorize quadratics into linear factors. You might have even factorized a cubic into linear and quadratic factors. Quartics often have no real roots, yet can be factored into two quadratics. Polynomials which can be reduced in this way are called reducible, because the factors are always of strictly smaller degree. But some polynomials can't, like this one, and we call them irreducible, and we mathematicians find them irresistible. Irrespective of that, I want to make clear that we're still only talking about polynomials with rational coefficients. So this here is irreducible. It can be reduced like this in the real numbers. But this isn't a valid reduction in the rationals, so for our purposes, x squared subtract 5 is an irreducible polynomial. Anyway, I claim the minimal polynomial is irreducible, and it's pretty easy to see why. Imagine if I could factor f into g times h, where both g and h have a degree less than that of f, then because alpha is a root of 0, then this product equals 0, meaning one of these must be 0, i.e. alpha is a root of g or a root of h. In any case, we've ended up with alpha being a root of a polynomial with degree less than the minimum, which is a big contradiction. Finally, what I think is the most powerful property of all, if I find any other polynomial with alpha as a root, then it is reducible, and moreover the minimal polynomial can always be extracted as a factor. So in other words, p of x is equal to f of x times g of x for some polynomial g. Now when I first saw this, it kind of blew my mind, because polynomials seem so chaotic. You can have as many powers of x as you like, and you can scale each term however you want, and here we find order. So we saw this result worked in that example, but why must it work in general? Well, divide p of x by f of x, and we get that p of x is equal to f of x times q of x, plus potentially some remainder polynomial r of x, where r of x is smaller in degree than f of x. This is a lot like Euclidean division of numbers, where the remainder is always less than the thing that you're dividing by. Now remember, p of alpha is 0, also f of alpha is 0, therefore r of alpha must be 0. The alpha is a root of the polynomial r, which has degree less than the minimum. So the only way this could be true is if r of x is the 0 polynomial, and so p of x has f of x as a factor as required. Now the real reason that I renamed this alpha wasn't really to save on a few syllables, although I do like doing that, is because everything we've just been through holds for a general algebraic irrational number alpha. It isn't specific to the cube root of 2. However, we can now use all this theory to show that the cube root of 2 cannot be the root of a quadratic with rational coefficients. So let's do that now. Well, suppose that it is the root of this quadratic. Since a degree 1 polynomial can't possibly be its minimal polynomial, if we divide through by a to make this monic, this must be its minimal polynomial. Now consider this polynomial x cubed subtract 2. We know the cube root of 2 is a root of this, but that means we must be able to extract the minimal polynomial as a factor, i.e. the minimal polynomial times something gives us this. That something must be linear, because degree 2 times degree 1 makes degree 3. It must also clearly be monic, as the other two are monic, so we can call it x plus t for some rational t. If this is identical to this, we can compare coefficients to establish a system of equations. And if we go ahead and solve this system, we get that r is equal to the cube root of 2. And that's a contradiction because r, we said, was a rational number, so can't possibly be equal to the cube root of 2. So the cube root of 2 is not a solution to a quadratic with rational coefficients, and what was the point of all of this again? Yeah, that's right. So that actually implies that these are independent, it can't be simplified, and therefore dropping the cube root of 2 into the rationals is in fact a degree 3 extension. Phew. I did warn you that the answers weren't easy, but stick with me because the best is yet to come. Because now we're starting to see a pattern. Square roots, the solutions to quadratics, increase the degree by a factor of 2. Cube roots, the solutions to cubics, they increase the degree by a factor of 3. Is this a coincidence? No. In fact, the degree of an extension by some irrational alpha is precisely the degree of alpha's minimal polynomial. And it's quite easy to prove this now, so first assume that q appended by alpha is a degree n extension. Well then these n terms must be independent. Otherwise, if it could be simplified, that means it isn't really a degree n extension. And if we take it all the way to alpha to the power of n, these are not independent. Otherwise, it would be a degree n plus 1 extension. So in other words, an expression involving these terms can be simplified. And that's if and only if we can find rationals that scale them and sum to 0. But if we can do that, then alpha is a root of that polynomial. So that means alpha is the root of a degree n polynomial and cannot be the root of a degree n minus 1 polynomial. In other words, the degree of alpha's minimal polynomial must be n, which matches the size of the extension. And the argument is similar when we run it backwards. If the minimum polynomial of alpha has degree n, then that necessarily means that these terms are not independent because we can find rationals that scale them and sum to 0, i.e. alpha's minimal polynomial. And it must mean that these terms are independent, otherwise that would mean the degree of the minimal polynomial is degree n minus 1. But if these n terms aren't simplifiable, that must mean we require n rational numbers to describe everything in this q extended by alpha, and therefore this is a degree n extension. Now this theorem will be essential going forward, because for example, suppose we want to determine the degree of q extended by some irrational alpha. Then all we need to do is find any polynomial with alpha as a root, and then factorize it. One of the factors must have alpha as a root, and therefore we factorize that. And one of those factors must have alpha as a root, and so on, and eventually we will hit on a factor which can't be reduced. So this is an irreducible polynomial for which alpha is a root. It must, due to uniqueness, be the minimal polynomial of alpha. Then whatever the degree of this polynomial, that will be the degree of the extension. I'll say at this point that these things are called field extensions, because Q is an example of a mathematical object called a field. Don't worry about that for now, but if you did want to read further, we are in a realm called field theory. Now it's time to use everything we've established so far to build up to the work of one of the great unsung heroes of mathematics, Pierre Wantzel. If you do need to take a quick break, now would be a good time, but come straight back, as we're about to assemble all of these pieces to finally solve those ancient problems. In my last video, I listed 3 problems that gave the ancient Greeks such a hard time. In 1837, Wanzel proved 2 of these. That's what we'll look at now, but note that the arguments I'll present are modernized to fit our current understanding, but they do appeal to the same theory as Wanzel's contributions. So why can't we double the cube? Well, take an arbitrary cube of length r, its volume is therefore r cubed, twice that is 2r cubed, and so the length of the big cube will be the cube root of 2 times r. So we can construct this cube if and only if we can construct this length, and that's if and only if we can construct the cube root of 2. So as always, we start with q. We know that the only irrational lengths we can construct involve a square root, and when we do, we expand our pool of lengths by a factor of 2. So we know that the degree of this extension will be 2 to the power of k. Now let's imagine that somehow, after a chain of all these extensions, the cube root of 2 is a member of this set. Could this happen? Could we combine a bunch of square roots to give a cube root? We want to say no, because this will somehow be something to do with a degree 3 extension, which would make it not a power of 2, but we've got to be careful. Sure, extending q by the cube root of 2 has degree 3, but who's to say that extending this field by the cube root of 2 is also degree 3? Because after all, this field already contains a bunch of irrational numbers. It's conceivable that sticking the cube root of 2 in there is maybe only a degree 2 extension. Well, to unpick this, we're going to simplify things and look at a more general result. Let's just take 2 irrationals, alpha and beta, extend q by alpha and say this has degree k, and now extend the resulting field by beta and assume this has degree n. My question is, what is the degree of q extended by both elements? I think our guts will want to say k times n, right? After all, earlier we saw that 2 degree 2 extensions came together to make a degree 4 extension. If that's what your gut is saying, then congratulate it, because it is right, but we do need to prove this. Well, pluck an element out of here, and we want to know how many rationals does it take to describe it. Since this is a degree n extension, this means that we need n elements from here to describe an element in there. And I'll call these elements b0 through bn-1. And I've written this sum vertically because now note that every one of these coefficients, or these bi, they are members of this, which is a degree k extension of q. That means each one will require k rational numbers to describe it. And I'll call these k rationals a0 through ak-1, and also add a second subscript so we know which bi it refers to. Unfortunately, I've had to use these awkward double subscripts here, but try not to worry about the specifics of the notation, and just realize what we've done. If we fold all of these betas inside these sums, we just end up with a giant sum of a bunch of powers of alpha and beta with rational coefficients. How many terms will there be? Well, there'll be k times n of them. This seems to hint at the idea that this is a degree kn extension, because a member of this needs k times n rationals to describe its position. But we also need to show that this can't actually be simplified. So let's do that now. Remember, this whole thing is simplifiable if and only if we can find rational coefficients that scale all of these terms to make 0. So, let's show that this can't actually happen. Let's assume that we found all of these AIs such that this whole thing is 0. But all of these betas must be independent because they form a genuine degree n extension over this field here. So all of the coefficients of these powers of beta must be 0. But now each of these sums are of k powers of alpha, and they are independent because they form a genuine degree k extension over q, so therefore all of these rational coefficients are in fact 0. So to clarify what we've done there, we've said that this whole thing was simplifiable if and only if we could scale each term to get to 0, but then we've just shown that the only way to scale each term to get to 0 is if every coefficient is 0, i.e. they are independent, it can't be simplified, so this is genuinely a degree kn extension. This result is called the tower law, as its repeated application can be generalized to any nested collection of fields. If k sits in L, sits in M, a so-called tower of fields, then the degrees multiply as we've just shown. Let's use this result now because remember where we were, a chain of square roots, and suddenly the cube root of 2 magically appears. But now consider this. Clearly the field which is just q extended by the cube root of 2 is nested between these two fields. But we know this is degree 2 to the power of k, we know this is degree 3, and we know this must be degree n, whereby the tower law 3 times n equals 2 to the power of k. And because a power of 2 is not a multiple of 3, this is impossible. This is why we can't make cube roots. This is the heart of construction impossibilities. Square roots simply cannot be chained together to make cube roots. They're almost a distinct class of irrational number. They behave differently. Squaring them yields another irrational, while square roots don't behave that way. The inclusion of a cube root simply expands Q more than what is capable with compass and straightedge constructions. We can also use these ideas to show that we can't trisect the angle. To show that a general angle can't be trisected, we just need to find one counterexample. In our case, we'll show that a 60-degree angle can't be trisected. Now, this seems totally divorced from all the stuff about cube roots and polynomials until we realize that cos 3 theta is equal to 4 cos cubed theta subtract 3 cos theta. Setting theta equals 20 and with some rearranging implies that cos 20 is a root of this polynomial. Then we're going to use this to show that cos 20 is impossible to construct, and that will imply that the angle of 20 is impossible to construct, because constructing the angle of 20 and the length of cos 20 are actually equivalent. Because, start with the circle of radius 1, if the 20-degree angle is possible, then we can project down to make the length of cos 20. On the other hand, if we started with a length of cos 20, then we just project up to create a 20-degree angle. So this is constructible if and only if this is constructible. If cos 20 is impossible, the 20-degree angle is impossible. Why is cos 20 impossible? Because this cubic is irreducible, which means that this is its minimal polynomial. And since it's degree 3, that tells us that cos 20 produces a degree 3 extension over q, and therefore it is impossible to construct for the exact same reason that the cube root of 2 was impossible to construct. Now the problem is that showing that this is irreducible is actually a non-trivial task. There are, however, a few tricks of the trade that we can employ in order to demonstrate this. Now this isn't really a video about the irreducibility of polynomials, so let me just state a few results that we'll use for the rest of the video. I'll leave the proofs on screen if you want to pause and read them, and in the extended cut of this video, I do prove them, and that's available to my patrons as a thank you for their support. The first is Gauss's lemma, because of course Gauss is going to show up again. Now this states that a polynomial is irreducible in the rationals, if and only if it is irreducible in the integers. So if we can't find an integer factorization, we can't find a general rational one. Next is this trick. A polynomial f of x is irreducible if and only if f of x plus a is irreducible for some rational number a. Now, this looks like it makes problems more complicated, but it is often used in conjunction with this final useful result, Eisenstein's criterion. This states that if you have a polynomial and you can find some prime number which doesn't divide the first term, divides everything else, and its square doesn't divide the last term, then it is irreducible. For example, this cubic here, 2x cubed plus 10x squared take 5x plus 15, this is irreducible because I can find a prime, namely 5, that divides everything but the first term, but its square 25 doesn't divide the last term. So let's go back to this cubic and consider swapping x for x plus 2. Expanding and simplifying, we have this. Choosing the prime p equals 3, we see that it divides every term except the first, but its square, 9, doesn't divide the last. So by Eisenstein's criterion, this polynomial is irreducible, and by this result, that means that this polynomial is irreducible. Therefore, this is cos 20's minimal polynomial, which is degree 3, so therefore it produces a degree 3 field extension on Q, and therefore cannot be constructed for the same reason that the cube root of 2 couldn't be constructed, and therefore the 20-degree angle cannot be constructed, and therefore a general angle cannot be trisected. Phew. A lot of steps there, but hey, if it were easy, it wouldn't have remained unsolved for 2,000 years. And now we'll conclude the video with Wantzel's last contribution, the answer to the problem that kicked off these videos. Which regular polygons can we construct with a compass and straightedge? Last video, I stated this theorem. A regular polygon is constructible if and only if it has a number of sides equal to the product of distinct primes times a power of 2, and where these primes are a power of 2 plus 1. When I first saw this result, I thought it was so mysterious and bizarre. Like, why can I take 2 to any power? Why can't we take these primes to any powers? And what do primes 1 more than a power of 2 have to do with anything? Well, now that I know the answers, I can't wait to share them with you. Gauss stated this, but he only actually proved one direction, that a polygon with this number of sides can be constructed. It took until Wantzel to prove that these are the only ones which can be constructed. So let's round off the video by showing that. First, we're going to generalize one of Euclid's results. Remember last time when Euclid showed us how to build a 15-gon using a triangle and a pentagon? Well, it turns out that that can be generalized. If m and n are coprime, that is, they don't share any factors, then an mn-gon is constructible if and only if both the m-gon and n-gon are constructible. Now, the first direction is straightforward, because if I have an mn-gon, then I can take every mth vertex and join them to form an n-gon. And likewise, if we joined every nth vertex, we would create an m-gon. But now for the other direction. Suppose that we can make an m-gon and an n-gon. Well, as we saw last time, we can embed them in a circle, and the existence of an n-gon implies that I can make an arc of 360 over n, and from the existence of the m-gon, 360 over m. And now we'll add them together. Note that so far we haven't actually used that m and n are coprime, so we'll use that now to say that there must exist integers a and b, such that am plus bn is equal to 1. This is a famous result called Bézout's identity, and if you want to know more about that, I made a whole video about this basic kind of number theory. Now what we actually do is we take b copies of this first arc and a copies and the second arc and see what happens when we add them. Now we can factor out that 360, this thing in brackets is 1, and so we've made an arc of length 360 over nm. And by duplicating that nm times around the circle, we will generate the vertices of an mn-gon as required. This allows us to simplify the problem because say we have some integer n and we want to know whether the regular n-gon is constructible, well then factor n into its unique prime decomposition, and so the n-gon is constructible if and only if the p1k to the nth gon is constructible, and this gon is constructible, the latter being constructible if and only if a p2 to the power of k2th gon is constructible, and this gon is constructible, and so on. So what we realize is that the n-gon is constructible if and only if the polygon with a side number equal to each prime power is constructible. Now our question becomes, which p to the kth gons are constructible? Well, here's where we bring back some theory from the last video. The vertices of a regular polygon are described by the roots of unity in the complex plane. If we want to make a regular polygon with p to the power of k vertices, we need to construct z such that z to the power of p to the kth is equal to 1. And then to see if it's constructible, we need to know its minimal polynomial. First, this whole z to the power of p to the power of k is a bit of a headache, so let's first consider the k equals 1 case, i.e. the pth root of unity. What's the minimal polynomial in this case? Well, we know that the roots of unity are spaced around the circle like this, with z, z squared, z cubed, right the way around to z to the power of p minus 1 somewhere down here, and then z to the power of p, which is 1. And recall that in the last video, we saw that they all sum to 0, and when we write this out, we see a hint at what the minimal polynomial might be, i.e. that z is a root of this polynomial. So this is some polynomial for which z is a root, but now I claim that this is in fact the minimal polynomial. Let's show that now. To show that it's minimal, we'll show it's irreducible, and these two results come to the rescue again, as well as a clever way to rewrite this that I touched on in the last video. Now watch what happens when I multiply this whole sum by z minus 1. We can see that most of these terms are going to cancel, apart from the z to the n here, and a minus 1 there. Last time I used that to show why the sum of roots of unity is 0, but this time I'll use it to show that this whole polynomial can actually be written like this. Another way to show that is to use the sum of a geometric series. Now let's use this result and we'll swap x for x plus 1. So this polynomial that I want to show is irreducible is actually the same as this. These ones will cancel, and now I can expand that first term there with the binomial theorem. These ones also die, and now dividing by x will just reduce all of the powers by 1. Finally, note that p choose p minus 1 is actually just p. And just for an added bit of clarity, I've just reinserted the penultimate term there, because now we observe something. Consider the prime p. P actually divides all of the terms except for the first, because it is known that p divides p choose k for any k. Just look at the pth row of Pascal's triangle to see that. And now, because there is a prime p that divides every term except the first, and p squared doesn't divide the final term, this is irreducible by Eisenstein's criterion. Because this is irreducible, the original polynomial was introducible by this result here, and so this is the minimal polynomial for a pth root of unity. So that establishes that this is the minimal polynomial for a pth root of unity, so the k equals 1 case, but what about for a general p to the power of kth root of unity? First, an intuitive explanation for where the minimal polynomial of a p to the kth root of unity comes from. Concentrate on the specific case of p equals 5 for now. We already know that this is the minimal polynomial for the fifth root of unity. And now the p squared root of unity, i.e. the 25th root of unity, looks like this. Some w where w to the power of 25 is equal to 1. But now we make an observation. W to the power of 5 is z, and this is z's minimal polynomial. So if we just insert w to the power of 5 in here, I will obtain a polynomial for w. Therefore we derive this polynomial for which w is a root. And the pattern continues. P cubed is 125. So if we take t, a 125th root of unity, notice that t to the power of 5 is w, and w to the power of 5 is z. So t to the power of 25 is z, so if we substitute t to the power of 25 into z's minimal polynomial, we'll derive a polynomial for t. In other words, t is a root of this polynomial. And the pattern continues if we wanted to, God forbid, take a 625th root of unity and so on. Now the choice of 5 didn't matter, so we can generalize this now. This is the minimal polynomial for a pth root of unity. For p squared, we replace x with x to the power of p. For p cubed, replace with x to the power of p squared, and in general, for p to the power of k, we replace x with x to the power of p to the k minus 1. And don't panic, I know this looks horrendous, but don't worry, we don't need to look at it for very long. So remember, we derive it by swapping x for x to the power of p to the k minus 1, and we can swap it in there as well to obtain an equivalent expression. Now we do the exact same thing as before, swapping x for x plus 1. Now the goal is to show that every term in here, apart from the leading one, is divisible by p so that we can use Eisenstein's criterion. This is just like before. But an equivalent way of saying that they're all divisible by p is that they're all congruent to 0 modulo p. Now note that x plus 1 to the power of p, we expanded earlier, was just x to the power of p, plus a bunch of multiples of p plus 1. So if we reduce this modulo p, all of these terms are congruent to 0, and we'll just be left with x to the power of p plus 1. Now what about x plus 1 to the power of p squared? Well, this is just x plus 1 to the power of p to the power of p. So we can raise all of our previous working to the power of p. But now look at what we've got here. This is exactly the same form as what we had originally, and we know that this will just wind up being congruent to x to the power of p squared plus 1 modulo p. And you can use a pretty simple inductive argument to say that x plus 1 to the power of p to the power of k will just be x to the power of p to the k plus 1. In fact, this is a special case of something known as the freshman's theorem, or the freshman's dream. So named because every freshman wishes it was this easy to expand a binomial. Applying this up here to the numerator and denominator, cancelling out the 1's, and dividing, we are left with this. So the fact that every term apart from the leading term is congruent to 0 modulo p tells us that p divides every term apart from the leading term. And now finally, there are p terms here. And if you were to expand all of them, you would get a 1 in each of these terms. So when we add those all together, we'll get a p. That will be the constant on the end. So if the constant on the end is p, p squared can't divide that. So this does satisfy Eisenstein's criterion with prime p, and therefore it is irreducible. Therefore this is irreducible, and therefore this really is the minimal polynomial for a p to the power of kth root of unity. And that is the degree of a field extension of a p to the power of kth root of unity. But remember, we can only construct with a compass and straightedge these field extensions here, which involve square roots. So if this p to the power of kth root of unity arises in here, what must the degree look like? Wait for it. Well, as we've just shown, the degree of this is p minus 1 times p to the k minus 1. We know that the degree of this entire extension is 2 to the power of n, and let's say that the degree of this extension is something. We don't really care what it is, because by the Tower law, this implies that p minus 1 to the power of p to the k minus 1 must be a power of 2. But if this product is a power of 2, that's only possible if these are both powers of 2. How can a prime to a power be a power of 2? Well, it must be the case that either the prime is 2, or that this power is 0, i.e. k equals 1. And in the case where k equals 1, we see that this whole thing disappears, and we are left with p minus 1 is equal to 2 to the m. Or that p must be a power of 2 plus 1. There it is. That's the connection to powers of 2. That's why the 17-gon is constructible, because it's 2 to the power 4 plus 1, but for example the 7-gon isn't, because it isn't one more than a power of 2. Amazing! And because of this k equals 1 condition, we can make a p-gon, but not a p to the kth gon for odd primes. K can only be greater than 1, we can only have a power of a prime in the case where p equals 2, which is why we can construct arbitrary 2 to the kth gons. And once we've made them, we can smush them all together by this result, giving us the Gauss-Wantzel theorem. There we go, finally. That was a lot of work to get there, so thank you so much for sticking with me. It's very technical, so you might be wondering, is there an intuitive explanation for why these are the only ones? The short answer is no, not really, because otherwise the proof would have been discovered much sooner. But I can sort of give you the gist of why the primes have to be in this form. Think back to the last video and Gauss's method. This only works for a prime gon, and that's because it's only with prime gons you can derive these nice Gaussian periods. Experiment with n-gons where n isn't prime and you'll see where it breaks down. Now if p is 2 to the m plus 1, that means there are 2 to the m non-trivial roots of unity. And it's in this situation where we can half them and half them and half them like we do with the 17-gon in order to make these nice Gaussian periods and therefore derive the root of unity as the result of a chain of quadratic equations. So that's my best explanation for the intuition here. So now do we finally have a complete list of constructible polygons? Well, as I said in the last video, surprisingly, no. But how can that be if we have this result? Well, think about which primes are actually one more than a power of 2. These are called Fermat primes. Yes, it's our old friend Fermat again. In fact, m itself must be a power of 2 for this to even have a chance of being prime, which is relatively easy to prove. And when m is a power of 2, we generate these numbers. You'll notice because of this double exponent, they get very big very quickly. Now, they became known as Fermat primes because he noticed that they always seemed to be prime, and he even conjectured that a number of this form will always be a guaranteed prime. But Euler managed to factorize this one, showing it wasn't prime. And in fact, to this day, these are the only known Fermat primes. We haven't found any more, and no one has proved that no more exist. So, a constructible polygon has a side number of that form. Exactly how many there are, we just don't know. So, I don't know about you, but I think this result is extraordinary. So, who was Pierre Wantzel, and why wasn't he famous for finally putting these problems to bed? Wouldn't people be ecstatic to see solutions to these 2,000-year-old problems, in the same manner that Andrew Wiles was celebrated for proving the near 300-year-old Fermat's last theorem? Wanzel was recognised for his talents at a very young age, earning the highest scores among applicants in 2 separate entrance exams of prestigious schools. While he was apparently an extraordinary teacher, speaking with unrivaled passion and clarity, he overcommitted and overstretched himself and, according to his contemporaries, never lived up to his potential. His friend Saint-Venant described Wanzel as quite a chaotic guy, sleeping very little, keeping no real routine, and misusing coffee. Which, sounds familiar. Wanzel also misused opium, and his death was blamed on his neglect of his health, and he died aged 33. I'm 33 next year, so that's kind of unsettling. But whether he lived up to his potential, he did prove these results. Why no fame for that at least? It's honestly tragic reading some of the correspondence between mathematicians 50 years later. They write, confused about whether the problem was actually solved, and if it was, by whom. In an amazing treatise on the topic, Jesper Lutzen offers several reasons why Wanzel was overlooked. These include the possibility that his work contained mistakes, but these are easily fixed or filled in, or that Wanzel merely scraped together pre-existing ideas of better thinkers like Gauss and Galois. But along with Lutzen, I reject this. It doesn't matter how small the connection was, nobody before him thought to do it, and sometimes a great discovery stems from that which others overlook. But Lutzen eventually argues that impossibility results were just kind of unfashionable at the time. It was an era of great constructions and solutions, but as Lutzen points out, Wanzel's proof does not provide a solution. A solution would have been a construction, but all Wanzel showed was that a particular type of solution does not exist. For example, Gauss's major contribution was constructing the 17 gun, and in a way that's more exciting, building something new for the first time in 2,000 years. Wanzel's result, on the other hand, could have been perceived as a bit of a party-pooping, don't bother trying to make anything new because it's impossible. Nowadays, it's incredulous to think that impossibility results were downplayed. Hilbert would later stress their importance. As Lutzen points out, they show how far one can get with a prescribed method within a given axiomatic system. In this case, the axioms are Euclid's postulates. This is how far we can get with regular polygons. But for me, it doesn't matter the purpose. Wanzel did solve these problems. It's not his fault that the results were of impossibility, that's just how the mathematics fell. I'm releasing this video on his birthday, the 5th of June, to commemorate his contributions. So, happy birthday Wanzel, thank you for your achievements. And thank you so much for watching. This concludes my double bill on constructible polygons. I may revisit this topic in future, as there is a really interesting twist on compass and straightedge constructions that you can add to allow for things like angle trisection. A massive thank you to my patrons who keep my channel afloat, and if you'd like to support me, you'll get your name in the credits, we can hang out on our dedicated Discord server, and much more, so see the link below. This has been another proof under another roof. Until next time.